Section 4 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Blaine Aiden McCoy, Riverside, California, January 2019. The neutron, nuclear spin. What Rutherford did not and could not take into account were the consequences of a completely new type of nuclear bombardment involving a type of particle unknown in the 1920s, though Rutherford speculated about the possibility of its existence. The beginnings of the new path came about through the reluctant realization that there was a flaw in the apparently firmly grounded proton-electron picture of nuclear structure. The flaw involved the nuclear spin. In 1924, the Austrian physicist Wolfgang Pauli, 1900 to 1958, worked out a theory that treated protons and electrons as though they were spinning on their axes. This spin could be in either direction, or, as we would say in earthly terms, from west to east or from east to west. Quantum theory has shown that a natural unit exists for what is called the angular momentum of this spin. Measured in terms of this natural unit of spin, the proton and electron have spin 1/2. If the particle spun in one direction, it was plus 1/2. If in the other, it was minus 1/2. When subatomic particles came together to form an atomic nucleus, each kept its original spin, and the nuclear spin was then equal to the total angular momentum of the individual particles that made it up. For instance, suppose the helium nucleus is made up of 4 protons and 2 electrons, as was thought in the 1920s. Of the 4 protons, suppose that 2 had a spin of plus 1/2 and 2 of minus 1/2. Suppose also that of the 2 electrons, 1 had a spin of plus 1/2 and 1 of minus 1/2. All the spins would cancel each other. The total angular momentum would be 0. Of course, it is also possible that all 6 particles were spinning in the same direction, all plus 1/2 or all minus 1/2. In that case, the nuclear spin would be 3, either in one direction or the other. If 5 particles were spinning in one direction and 1 in the other, then the total spin would be 2 in one direction or the other. In short, if you have an even number of particles in a nucleus, each with a spin of plus 1/2 or minus 1/2, then the total spin is either 0 or a whole number, no matter what combination of positive and negative spins you choose. The total spin is always written as a positive number. On the other hand, suppose you have lithium-7, which was thought to be made up of 7 protons and 4 electrons. If the 7 protons were all plus 1/2 and the 4 electrons were all minus 1/2 in their spins, the nuclear spin would be 7/2 minus 4/2 equals 3/2. If you have an odd number of particles in the nucleus, you will find that any combination of positive and negative spins will never give you either 0 or a whole number as a sum. The sum will always include a fraction. Consequently, if one measures the spin of a particular atomic nucleus, one can tell at once whether that nucleus contains an even number of particles or an odd number. This quickly raised a problem. The nuclear spin of the common isotope nitrogen-14 was measured accurately over and over again and turned out to be 1. There seemed no doubt about that, and it could therefore be concluded that there were an even number of particles in the nitrogen-14 nucleus. And yet, by the proton-electron theory of nuclear structure, The nitrogen-14 nucleus, with a mass number of 14 and an atomic number of 7, had to be made up of 14 protons and 7 electrons for a total of 21 particles altogether, an odd number. The nuclear spin of nitrogen-14 indicated even number, and the proton-electron theory indicated odd number. One or the other had to be wrong, but which? The nuclear spin was a matter of actual measurement which could be repeated over and over, and on which all agreed. The proton-electron theory was only a theory. It was therefore the latter that was questioned. What was to be done? Suppose it is wrong to count protons and electrons inside the nucleus as separate particles. Was it possible that an electron and a proton, forced into the close confinement of the atomic nucleus, might, by the force of mutual attraction, become so intimately connected as to count as a single particle? One of the first to suggest this, as far back as 1920, was Rutherford. Such a proton-electron combination would be electrically neutral, and in 1921 the American chemist William Draper Harkins, 1873 to 1951, used the term neutron as a name for it. If we look at the nitrogen-14 nucleus in this way, then it is made up not of 14 protons and 7 electrons, but of 7 protons and 7 proton-electron combinations. Instead of a total of 21 particles, there would be a total of 14. Instead of an odd number, there would be an even number. The structure would now account for the nuclear spin. But could such a revised theory of nuclear structure be made to seem plausible? The proton-electron theory seemed to make sense because both protons and electrons were known to exist separately and could be detected. If an intimate proton-electron combination could also exist, ought it not exist or be made to exist outside the nucleus, and ought it not be detected as an isolated particle? Discovery of the neutron. Throughout the 1920s, scientists searched for the neutron, but without success. One of the troubles was that the particle was electrically neutral. Subatomic particles could be detected in a variety of ways, but every single way, right down to the present time, makes use of their electric charge. The electric charge of a speeding subatomic particle either repels electrons or attracts them. In either case, electrons are knocked off atoms that are encountered by the speeding subatomic particle. The atoms with electrons knocked off are now positively charged ions. Droplets of water vapor can form about these ions, or a bubble of gas can form, or a spark of light can be seen. The droplets, the bubbles, and the light can all be detected one way or another, and the path of the subatomic particle could be followed by the trail of ions it left behind. Gamma rays, though they carry no charge, are a waveform capable of ionizing atoms. All the particles and rays that can leave a detectable track of ions behind are called ionizing radiation, and these are easy to detect. The hypothetical proton-electron combination, however, which was neither a wave form nor a charged particle, was not expected to be able to ionize atoms. It would wander among the atoms without either attracting or repelling electrons, and would therefore leave the atomic structure intact. Its pathway could not be followed. In short, then, the neutron was, so to speak, invisible, and the search for it seemed a lost cause. And until it was found, the proton-electron theory of nuclear structure